Hello everyone. So in this video we're going to be going over something called integration by parts. So this is an integration tactic that we can use when we are faced with an integral that it's not something easy like the integral of sine or the integral of e to the x or something like that. And it's also an integral that integration by substitution doesn't work. So if we keep attempting different forms of u substitution and we don't get anything out of them, we can try integration by parts as kind of like a backup strategy to evaluating an integral. Now, remember the reason why we introduced integration by substitution. It was because if we selected this variable u that was within our integral, we could actually rewrite the integral in terms of that variable u to represent the same integral but in a simpler form, so it was easier to evaluate. And in integration by parts, we're trying to do the same thing, but it's a little bit more complicated than integration by substitution because we're actually looking to define two variables. Whereas in integration by substitution, we just wanted that variable u. In integration by parts, we're looking for a variable u, but also a variable dv. So a little bit more complex, but there is a good thing about integration by parts, and that's that the way we solve the integral is a little bit more sequential. So really, if we can come up with these variables u and dv, that's the hardest part. Everything after that is kind of just following a step-by-step procedure. But basically, most textbooks don't show integration by substitution in this way. I like to, because generally, what should clue you in, I'm sorry, integration by parts, not integration by substitution. But going back to what I was saying, what should clue you in into when you should use integration by parts is a lot of times it's going to be when you have one function multiplied by another function. And recall that, let's say we had something like the integral of x e to the x squared dx. Well, this would be a case where we would use u substitution because we see a function and something similar to its derivative inside everything. Now, the first example that we are going to look at when we do integration by parts is if we have something like this. Now, this doesn't look much different than the previous function, but notice now we don't have that function derivative relationship anywhere. I can't say u equals x because then du is going to be dx, and I have no way to take this into account. This would end up, if we switched u's for x's in this case, we'd end up with just getting the integral of x times e to the u du, which is the exact same integral we had before. So really, the way you guys should think about integration by parts is sometimes you can recognize it by if you have one function multiplied by another function, but it doesn't always have to show up in this way, but a lot of times it does. So sometimes this can be a clue to when you would need to use that. And again, it's when we have one function multiplied by another function, but we don't get that function and something similar to the derivative relationship that pops out. Mainly, I would say you want to use integration by parts when you basically just can't find a u substitution that works. Now, just with u substitution, this stuff is pretty tough when you first do it. It can be very difficult, so I would highly recommend rewatching this video or coming to see me to do example problems in the book to get practice. But just like with u substitution, the more practice you get, the quicker you actually recognize when you have to use integration by parts or u substitution or even some other different method of integration that we haven't covered yet. So anyway, integration by parts is basically this. What we want to do is we want to reduce some integral into the integral of some function u multiplied by some function dv. And that dv is going to contain our dx, our differential operator that's inside there. So in this case, for this integral that we have right up here, in this case, our function u is just going to be our function f of x, and our function dv is going to be g of x times dx. Remember, the dv, we always need to have a dx that's associated with that on the other side. So we can write this integral as something like this. And it turns out any integral can be written in this form. Even if we have the integral of just dx, well, in this case, u is equal to 1, and dv would just be dx. So no matter what the integral we have, we can always write it in this form. Now, the tricky part is, can we actually apply integration by parts to it? That's something that is not guaranteed for every single integral. All right, so again, we're taking one integral and we're trying to find this variable u and this variable dv. And so in integration by substitution, we would find a variable u and we would take the differential of it to help us in our substitution. Now in integration by parts, we do something a little bit different. We do this step, we find u and we take the differential of it to get du, but we also have dv. And what we want to do with dv is we actually want to integrate that to get what the variable v is equal to. So in integration by parts, we're making a substitution of variables, and in one of those, the u variable, we're differentiating it, and in the dv variable, we're integrating it. So we're doing two different things. So here it basically just shows you if we had this function f of x g times g of x dx, we would again say that u is equal to f of x, so du would just be f prime of x dx. Remember, when you're doing differentials, you always got to add that dx or du or dt or whatever to the end of your derivative. Now, if dv is g of x dx, if we take the integral of dv, well, we just get v. So we got to take the integral of that function that we selected for dv in order to get v. And then we have the four components v, du, u, du, v, and dv. And you'll see on the next slide how we use these four variables to evaluate an integral. So what we do is, again, if we break everything up, recall that in this case we said u was f of x and dv was g of x dx. How we evaluate this integral, which again we set up as this integral is no different than the integral of u times dv, is going to be u times v minus the integral of v times du. And just as with integration by substitution, our goal in integration by parts is we want that integral to be simpler than the original one we started with. If it's more complex, it means we picked a bad u and a bad dv, and we got to start all over again and pick a different one. Now, I will give a fair word of warning. Be prepared to spend a lot of time solving these problems. The solutions do not come quickly, especially when you're just starting out. Now, when you've had some practice, you might be able to do them kind of quick, but expect to spend a decent amount of time on doing an integration by parts problem. They are not really straightforward and really easy to do, so just be prepared for that when you're trying to work on some of these on your own. All right? So let's look at an example of doing this, okay? And in this one, I'm going to work out this example. I'll probably actually work out all three of these examples just on my own. But if you want to, go ahead and pause the video and see if you can pick a u and a dv that makes this thing work. And remember, what you're trying to do is get this integral on the left-hand or on the right-hand side to be easier to solve than this integral on the left-hand side. So give it a shot. If you're really stuck, just keep going with the video and you'll see how we split up this particular integral. All right, so if you gave it a shot, or if you're just like, this is blowing my mind right now, I just want to see how it's done, I'll show you how it's done. So let's look at actually a case of when we pick a u and a dv that doesn't work first, and we can kind of see how when you get a more complicated integral on the right side, you know immediately, oh wait, I chose the wrong thing, let's try something else. So let's say in this case, let's make u equal to e to the x and dv equal to x dx. So recall that u times dv gives me my integral right here, x e to the x dx, okay? So you got to make sure you choose your u and your dv so they represent everything that's inside that integral, all right? So to get du, I differentiate e to the x, so du will just be e to the x dx. And to get v, I must integrate dv. So the integral of x dx will just be 1/2 x squared. And in this case, we don't worry about the plus c, okay? So when we're doing this, yeah, just forget about that plus c. We don't ever put it in there. So if we put this u, du, v, and dv into our integration by parts formula, what we end up getting is u times v is e to the x times 1/2 x squared, then minus the integral of v du. So this will be the integral 1/2 x squared times du is e to the x dx. And immediately you can see, compare this integral to the one we started with. The integral we got now is more complicated than the one we started with. So basically, we picked a bad u and a bad dv. All right. So now that you've actually seen me do this real quick, why don't you pause the video and see if you can pick a u and a dv that ends up giving us a nicer integral on that right-hand side than we had before. So pause the video and actually try to solve this. Give it a shot. Okay, so the correct u and v to choose here would be, let's say if u is equal to x, du would therefore just be, actually, let me just give you the u and the dv. Or actually, let me just give you the u, okay? Let's try that. I just gave you a u of x. Now you got to figure out what dv would be, and you got to find du and v as well. Then try to plug it into this formula. So pause the video and give that a shot if you did not select u is equal to x before. Okay, so if you tried this, well, if u is equal to x, dv has to be the rest of the stuff in that integral, including the dx. So it will be e to the x dx, okay? So if we want to get du, that's just going to be dx. And if we want to get v, well, the integral of e to the x is just e to the x, so that'll just be that right there, okay? So if you didn't get to this stage, pause the video again and try to rework the rest of this integral using this u, du, v, and dv. Okay, so if you gave it a shot, if we plug our u, du, v, and dv into the equation for integration by parts, we get this integral is going to be equal to u times v, which will be x times e to the x, then minus the integral of v du. V is e to the x, and du is dx. So now take a look at this. Wow, that's a lot simpler integral to solve than the original one we got. So we're on the right path here. We're doing a good job, okay? So therefore, if we solve this integral, this will just be x e to the x minus e to the x, and now at the end we can add our plus c. So that would be the solution to this integral. And again, if you don't believe it, try taking the derivative of this solution. You'll end up with just x times e to the x. Remember that check that we always have to make sure we're doing this correctly, okay? So I'm actually going to stop this video right now, give you guys a chance to re-watch this, kind of absorb this a little bit more, and in the next video I'm going to go over 2 more examples of integration by parts.